Odin, like a lot of modern languages, has reflection, which is the ability for code to look at itself. Now, some languages take this super far, allowing you to modify code at runtime or create dynamic values, but in most languages with reflection, it is limited to type introspection, and Odin does the same. If you do want AST level control, you probably want metaprogramming tools, such as the parser found in core Odin. If there's enough interest, I can definitely make a video covering that as well. Different languages' reflection approaches can generally be split into two groups, runtime and compile time. Compile time reflection has some benefits, like integrating nicely with generics and other features that most languages already have for some amount of compile time type information. But it has a huge downside of complexity. In order to have good compile time reflection systems, you need to be able to run arbitrary code at compile time, which requires a lot more work. Some languages, like Zig and C++, already have this, and so they can get away with compile time reflection. But Odin is a much simpler language, and it's hard to beat runtime reflection when you're aiming for simplicity. In Odin, the compiler will generate type information for any type that needs it. Determining if a type needs reflection information is pretty simple. It's only required if you use it in combination with the any type, or if you explicitly request that information via the type info of built-in. I want to really stress this point, because a lot of people seem to mistakenly think that Odin uses reflection everywhere, when that's not true at all. The language itself, the runtime, never uses reflection. It's only used when you explicitly want to use it. Some examples of where reflection is used inside the standard library include printing and serialization, which are massively helped by runtime reflection. Doing it at runtime means error checking is a lot easier, and you don't have to duplicate function implementations for every type that you print or serialize. Any is Odin's reflection type. It's nothing special in reality, just a pointer into type ID, but it exists so that regular values can implicitly upcast. The way Odin stores this type information is with the type table, a hash map that's filled in by the compiler. For every type that needs reflection information, the compiler will generate it and throw that info into the table. Then, the values of that hash map are exposed via the language runtime. Directly accessing this table isn't very useful though, since it's sparse and in no particular order. Odin has a special type called a type ID, which is a value that represents a type. The actual value of these type IDs are the hashes used by the hash map to do the lookups, and it's what internally happens when you call type info of. Now, I'm going to walk through the process of using reflection to do some basic serialization. We'll implement a few procedures that allow us to turn arbitrary data into JSON, using reflection to do everything automatically. There won't be any deserialization here, since that's a lot more complicated, but after watching this video, you should be well equipped enough to read the implementation inside of Odin's core library if you're interested. We also won't be doing any proper error handling for simplicity, and I'm going to avoid the core reflect package, which could provide some helper functions, because my goal is to showcase the raw structure of this reflection data. Now, let's get started. On json.org, we can see the full JSON specification twice, once as a formal grammar and once through flowcharts. Using this spec, we can get a feel for what we're going to implement. First, the top-level procedure for turning everything into JSON using the any type. Then, implementations for all of JSON's basic types: objects, arrays, strings, numbers, and booleans. We aren't including null here since it's not a type in Odin. We'll need to add a lot more procedures along the way, but let's start from the top with implementing toJSON. The JSON spec says that the top level of a JSON file can be any JSON value. So we're actually just going to set up our builder and call our writeValueProc here. First, we'll get the base info of our type. Base here just means we're removing any distinctness, including named types. Next, we'll add a switch statement that'll determine what type of value we actually want to write. The easiest case is the named case, since that would only trigger if the runtime was broken. We'll add a panic and move on. Next, we'll implement strings, since they're the next easiest. TypeInfoString here covers all 4 types of strings in Odin, and that's an important thing to keep in mind with Odin's type infos. They don't represent individual types. That's what type IDs are for. Type info is about categorizing the different types of types, like strings, structs, or integers. We're also throwing in type info rune here, since JSON does not distinguish between characters and strings. One more feature of Odin's any type is that you can use it to do type switches, like you would with a union. We'll use this in the future to check which concrete type we're working with, and Odin automatically handles the casting for us thanks to the type switch. For now, we'll bunch all 4 strings into one case, and we'll also add a panic for any non-string type, since that shouldn't be possible. If it does happen, it would mean that Odin added a new string type or something, and we'd rather not pass silently in that case. We'll use some of the procedures in core format to handle actually writing this data to the buffer. You might consider that cheating a little bit, since it'd be easy enough to do this ourselves for strings, but something like a float to string converter is definitely out of scope for this video. If you don't know about the %q format specifier, it just handles quoting the string and unescaping certain escape sequences. We also need to be careful about %q with the runes, since core format will use single quotes for this. There's a way to just write the escape rune directly, but it does require we go through the writer interface. We'll cover numbers next, at least the basic ones. Quaternions and complex numbers won't be implemented here. The integers are easy enough. There's no tricks here, just a lot of different types. We'll also add a similar panic to we add for strings. Floats are a bit more complicated. Less types, thankfully, but we're forced to have some special handling. JSON numbers are not IEEE floats, so they don't support nan or infinity. This makes it somewhat non-obvious what to do in those cases, and there's no perfect answer. We'll just use strings in this case, and we're going to have to do some slightly weird stuff in our switch statement, since we need to cast all these up to f64 for consistent formatting. Once we've got that, we can use math.classify to know exactly what type of number we're working with, giving special handling to the infinities and nan. This one's dead simple. We just need to be a bit careful and remember that Odin actually has 5 different bool types. Because of that, we're taking a similar approach to floats, where each arm casts. Now, let's get into the interesting things. The code here might get a bit ugly, but it's also super cool. We're going to implement writing structs, which should be enough for us to get a basic implementation up and running. We can iterate over every field in a struct in a few ways. The easiest would be to use struct fields zipped from core reflect, which gives you a nice SOA array with everything in it. But since our goal is to get a feel for how this reflection data is actually structured, we've been avoiding that package. The type info includes the number of fields, which we can use as an index on all of the other info fields we need. Getting the name is easy, but how do we get the values? Since the type info provides a field offset, and any is a pointer internally, we can easily get the address of the field by adding them together. Now we have to assemble our own any with a custom pointer and type ID. These procedures could be enough for a lot of basic types already, but I'm going to keep going and support a few more types. Odin has a lot of different array types, but let's start with fixed arrays. Arrays aren't too different from structs, but since they only store one type, they expect us to calculate all the offsets ourselves. We'll do slices next, since that's the array type you see the most. It's pretty similar, but since length isn't part of the type here, we're going to have to do some nasty casting. Internally, all slices use the same representation, just a pointer and a length. That structure is exposed via runtime.rawSlice, so we're going to do a pointer cast and use that to get the length. We also need to use it for the pointer to the items, since the address of the slice is not the same as the address of its data. Dynamic arrays are an interesting case. Their type info is identical to slices, and if you saw my last video, you'll know that you're able to pointer cast dynamic arrays to slices because of the guaranteed memory layout. Because we're already doing a pointer cast inside our write slice call, we can totally reuse that same call and cache the type info. Because of how Odin represents maps, reading out of them with reflection gets pretty ugly. I'm implementing it here for completeness, but feel free to skip this part if you want. First, we do another pointer cast to get our hands on a raw map. Then, we use a procedure from runtime to get opacity. Next, we get the key and value info and pointers to the keys, values, and hashes. We use that type info base procedure from earlier to make sure we're using string keys, and if we aren't, we panic. This is the first user error we've hit, and in any real program you'd want to actually return the user an error here. Now we start our loop. Note that because these are hashes, there's no guarantee on the order of the keys. We just go over every index in the map's capacity and use that to check if the current cell has something in it. If it does, we get a pointer to the key and the value, assemble some any's, and write them. Enums are pretty simple. We start by doing the same integer upcasting as usual. Based off of the enums underlying type, the only difference is that I'm using the autocast keyword, just to avoid the long type name. Then, we just walk through all the variants and check which one we're working with. If we find it, then we write the name, and if we don't, then we just write the integer value. The last thing we're going to implement is support for unions. There's a couple of different ways to do this, and the best way depends on how you're actually using the union. You could make this configurable, but I'll just go with directly writing the data of the variant, or null if the union is empty. First, we need to figure out what variant of the union we're actually using. The type info tells us what type the tag is and where to find it, so we can use that to pull it out into an integer. First, we'll make an any and use a type switch to pull it out. There's a procedure in core reflect that does the same thing, and it's basically identical. Unions are able to be tagged with no nil, which means the 0 tag just refers to the first variant. If our union isn't no nil, then it's the 1 tag that's referring to the first variant, so we subtract 1 to get a proper index. This also gives us a nice -1 to represent a nil union, so that's when we write null. Now, we get a pointer to the data. You'll notice that the type info doesn't store the offset anywhere, and that's because the union data always has 0 offset, so we already have the pointer. Then we just write the variant and we're good to go. The last thing we need to do is add a catch-all for unsupported types. Ideally, this would return a proper error, but that's out of scope for this video, so we're just gonna panic. This parser is super basic, and it has a few problems, but it should get you a good feel for how to use reflection. If you want to see something more advanced, check out json.marshall from core encoding/json. There are a few reflection features that I didn't touch on, like struct field tags, but that's mostly handled inside of core reflect. The general idea is that you're able to attach strings to a struct's fields, which are accessible through reflection. It's also important to note that although the Odin compiler supports custom directives and attributes, those aren't accessible in reflection data. Instead, they're meant to be used by the parser in core Odin. If you want to check out the full source code, I've open sourced the entire project with a link in the description. Now, if you've made it this far, you might want to subscribe. I'm trying to make helpful videos every week to teach people about low-level programming and programming language design. If this video was helpful, leave a like, and feel free to comment any suggestions. As always, the pinned comment will have any corrections. Bye bye.